Thanks for coming along. It's a pleasure seeing so many of you. So I'm going to be talking about work I did on reverse engineering a piece of software provided by a vendor for configuring systems. Now, I've previously written about this publicly, and therefore you may be able to figure out which vendor it is. I prefer it were you not to attach the name of the vendor to this presentation in an obvious manner, for reasons that will become clear later on. I've also been informed that I am not permitted to swear. If I suddenly go very quiet, then you can read into that as you will.
Is the limitation only to the English language?
Right, Ben, I am not going to swear in French either. Yeah. Anyway, deploying servers is a fairly tedious activity. If you want to roll out, say, several thousand servers, then not only do you have to physically take servers into a hosting facility, physically plug cables into them, you then potentially have to physically attach a keyboard and monitor in order to perform firmware configuration and make sure that they're configured to your requirements. For instance, it may be that you don't want hyperthreading enabled because you have performance concerns, or your particular workload doesn't deal well with hyperthreading. It may be that you want a TPM to be turned on. It may be that you need to use AHCI rather than a legacy IDE, or vice versa, that kind of thing. We pay people to do this, and I assume that they live fairly sad and unhappy lives. So the obvious flip side to that is that automating server deployment is awesome. It means that these people do not have to go and touch large numbers of individual servers and poke things into them. Instead, you can just rack the servers. Unfortunately, so far, we haven't found a way of automating that. You have to plug the cables in, you turn it on, and then you, via some automated mechanism, roll out all the firmware configuration. And that means that the people who formerly had to spend their days standing there configuring systems can instead be made redundant. Which is possibly a win, depending on how you're looking at it. So there's a few different mechanisms for doing this. The most straightforward and traditional one is over a serial console. Most server-level firmware will allow for firmware serial redirection, as well as just providing a operating system level serial console. And that means that you can typically drop to some sort of configuration interface over serial. This allows you to modify configuration settings. However, anyone who's ever tried to write a configuration script using expect, something that sees input and then pokes output, will know that it's painful enough doing that when you're running over std.io, and doing it over serial instead is going to be absolutely miserable. So you could do it that way. It's not particularly attractive. Vendors gradually started realizing that some sort of standardized mechanism for doing this would, of course, be completely inappropriate because that would remove vendor value add. So they all came up with their different ways of doing it. Even when they are using the same standards, they all have different schemas on top of that standard in order to ensure that it's almost impossible to write a piece of software that can configure multiple different vendor machines, so you end up locked into anyway. Several systems now offer a web services interface that allows you to make API calls and get back the current configuration state and push a new configuration state into the system. And then there tend to be various vendor-specific methods. Sometimes these run on the local system even, so they make vendor-specific calls to the firmware in some completely undocumented way, which then permits you to modify configuration options, and then when you reboot the system, the new configuration options have been applied. The vendor in question supplied a tool that did this. It is a small, well, it's not actually particularly small. It's a 250 kilobyte binary. You run it on the system that you wish to configure, or on an example of the system that you want to configure. And it spits out an XML file. And the XML file contains every configuration option, the current value, and the possible values. You then modify the XML file, and you set configuration values as you want. You feed that back into the tool. It does some magic. And then when you reboot the system, the firmware is now configured in the way that you requested. So this means you can, for instance, turn on TPM, change the hard drive settings, change the boot priorities. And then all the systems can boot. If they're configured to netboots, they can netboot the first time. You can feed them a small provisioning environment that runs this tool, configures them appropriately, and then reboots them, and they're then appropriately configured. Downside is that it's a 32-bit binary. Now, for our specific case, I should give you a little bit of background. Nebula, we make a box, you put it into a rack, you plug a bunch of servers into our box, you turn it all on, and it automatically deploys stuff to them, and you have an OpenStack cloud. Now, some of our security work has focused on taking advantage of firmware-level features, like using TPM. Server vendors tend to ship systems with the TPM disabled because people still have privacy concerns over them. So it's more convenient for us if we can tell customers, yes, these new features can automatically be used in your system without you having to physically change firmware options. We can upgrade the cloud controller, you reboot all the nodes, and suddenly they have a new firmware configuration. That's the ideal scenario. We can turn on firmware options as we require them. We don't ship any 32-bit libraries, because why would we do that? So having a 32-bit binary was not particularly useful to us. I, as a result, decided that we should figure out what this binary did and then re-implement it, and then we would be able to do this without having a 32-bit binary. So the first thing you do when you have a user space binary and you want to know what it does is you run it under strace. And strace is, if you haven't heard of strace, it's a tool that intercepts every system call that an application makes, and then dumps the system call and the arguments to standard output. And that means you can see every file that an application opens. You can see every read or write it performs to any open files. You can see ioctls it uses. So kind of expectation I had was that this utility would open some kind of hardware interface and then do some reads, writes, ioctls to it, and I could simply monitor those through strace and then reverse engineer its protocol. So firstly, I assumed that it would be speaking to the baseband management controller over IPMI. IPMI no, I'm not actually planning on swearing here. I was trying to remember what IPMI actually stands for, but I don't know. Anyway, it's awful. IPMI is a management, the MI stands for management interface. It's a standardized mechanism for talking to devices. Ben, do you have something to say?
Quick question. None of those servers provide an IPMI direct interface on the network.
OK.
If you like being hacked.
Right. So the question was, does the IPMI thing provide an access method via a network connection? In this specific case, the vendor provides a network connection that you should obviously have connected to an entirely physically separate network. This is not in any way connected to the outside world. But they do not have an API for configuring systems over it. So at this point, this vendor only provides, this is the only method for configuring these systems. So I assumed that it was going to use IPMI, which is a standardized mechanism for speaking to devices like baseband management controllers, the service processors that monitor your system. They're typically actually small Linux computers inside your computer. That should scare you. But it wasn't accessing /dev/IPMI, which is the kernel interface to IPMI. So it wasn't sending any IPMI commands to the IPMI hardware. So, OK, well, there's no fundamental reason why they would use IPMI. It would be the obvious way of doing it, but maybe they're doing it in some cleaner manner. The service processor also appears as a PCI device. So I thought, well, OK, maybe it's accessing PCI configuration registers. No, it does not touch anything under /sys/bus/PCI, and it doesn't touch the legacy one under /proc either. So it's not doing PCI access via the kernel. As a result of this, I thought, well, OK, it must be doing some sort of memory mapped access. And the kernel has a feature called MMIO trace. MMIO trace means when an application attempts to map a PCI memory area, the kernel doesn't really map it. When the process then tries to access this PCI device, the kernel can catch that access, dump it, and then send it through to the hardware. And that means you can see all the PCI accesses that a tool is performing. It's not limited to PCI. You could also do the same for any part of address space, but typically applications doing this use PCI. So this was used heavily for the NVIDIA driver reverse engineering that was used to produce the Nouveau driver. MMIO trace meant that they could see all the accesses that the binary NVIDIA driver was performing to the hardware, and then they could reverse engineer the command string from there. No, I configured MMIO trace. It's part of the stock kernel now. It's under debugfs. It's pretty brilliant. But there was no access to any PCI space. So overall, at this point, we know it doesn't use dev IPMI. It does not use any of the standard PCI configuration space access methods. And it does not just map a PCI register region directly and then read and write to it. In fact, this tool does not use any kernel-provided hardware access. Now, this is a little bit strange. And once I'd come to this realization, there was only really one thing to do. After some consideration, I went back and looked at the strace logs again, because a user space binary, even if running as root, is by default not allowed to perform any hardware access. Well, that's not entirely true. It could use USB stuff. I also checked that it wasn't doing any USB accesses, just in case. But the device doesn't appear on USB, so that would have been very, very strange. I looked at the strace logs, and I saw that it was calling IOPL. Now, IOPL allows you to set the privilege level for I/O operations. And this means that you can then access from user space port-based I/O, which is something provided on PC hardware. You have the memory bus, and you also have the I/O bus. The I/O bus is a straightforward method for accessing hardware. It's low performance, it's low bandwidth, but it's a single instruction to read something, and it's a single instruction to write something. So it allows you to design very simple hardware. It allows you to write very simple applications. It's a really bad sign to see this called. Really, really bad sign, because at this point, you know that the application is doing hardware access itself without asking the kernel for any assistance. So the problem with an application that does in and out I/O port writes is that those are not, they're executing directly on the CPU. They're not system calls. And so you can't follow them using strace. There's no way of just trapping them and seeing that that's happened. So my initial approach was to instead use GDB. And I ran nm on the binary, which gave me a list of the symbols in the binary. And I saw that it had its own in and out functions. So I set GDB breakpoints on those. And then I wrote a small GDB script that meant that every time it hit one of these breakpoints, it would print the arguments to the function, print the function name, and then continue. And that meant that I could see every in and out that it was performing through these function calls. And that meant that I could see all the hardware accesses it was performing. So excellent. I can now actually see what this application is doing. And then I realized I really wished that I was not able to see what this application was doing, because it's really, really, really awful. So this time I am failing to swear. Now, a small digression. PCI devices have two main ways of accessing features. You have register space that is typically memory mapped or can even appear in I/O space. And then you have PCI configuration registers. And you need PCI configuration registers to do things like map the memory regions into the memory map. You need to tell the PCI device where it can actually fit itself in address space and make sure that it doesn't conflict with anything else. You often also have some low-level hardware configuration that's performed via PCI configuration space. Now, the firmware needs to do the initial PCI configuration. And the firmware at this point is running very early in the boot process. The firmware does not have a great deal of intelligence available to it. So the firmware needed a very easy way to configure PCI devices. And the way you do that is you take the device address and the register you want to access, and you map all of those, you pack all of those into a 32-bit value, and then you write that 32-bit value to OXCF8, which is an I/O port. OXCFC at that point will then be mapped to the register you requested on the device you requested, and you can read or write from OXCFC. So you read the value you want, and then you write it back. The kernel still does this for the majority of PCI devices. PCIe provided a better way of doing this. The other thing that limits this is that with this mechanism, you can't have more than 256 PCI configuration registers. PCIe added more, so it needed this other way of handling them. But that's kind of out of scope here. Now, looking at this, there's kind of an obvious problem. You write to CF8, and then you read and write to CFC. Now, in between you writing to CF8 and you touching CFC, what happens if something else touches CF8? And the answer is that you read or write to the incorrect register, which is probably upsetting. So there obviously are mechanisms to prevent this from happening. And unfortunately, all of those mechanisms are implemented in the kernel. And if you're not using the kernel, nothing prevents this from happening. If you ran 2 copies of this utility at once, for instance, you would end up with incorrect values being written. But even worse, if the kernel itself decides to touch a PCI configuration register while you're running this tool, which the kernel is allowed to do because it's the kernel, then again, you'll just write over arbitrary, well, not arbitrary, well-defined. You will not write the stuff you expected to write. And potentially you will, in the best case scenario, you will end up writing to a different device, and you will end up just putting most configuration registers get ignored. Worst case is the hardware suddenly behaves weirdly and the kernel crashes or the bus crashes and your system falls over. The absolute worst case, though, is the kernel writes to CF8, you write to CF8, and then the kernel writes something into the register that you were just about to write something into. And then suddenly you've just written a completely invalid configuration value into your system firmware. And it's likely that your vendor didn't actually test the system to make sure that this wouldn't cause problems. So you could perhaps now end up with a system that decides to try to program its memory clock to a couple of terahertz. And that is going to cause you problems later on. So that was pretty bad. I was a little bit upset at this point. But it wasn't just touching PCI configuration space. Some of the values changed PCI configuration space, but some of the values performed access to the system CMOS region. And the CMOS region is where traditional firmware configuration values were. It's part of the real-time clock hardware on a PC. And there's 2 I/O ports to access it. There's an address port and a data port. You write the address, and then you read or write the data. And you can see that maybe this has the same kind of problem as we just talked about. Because, again, the kernel will tend to access the CMOS in order to do things like read the time from the clock. And Yeah, Ben suggests that you should not run this configuration utility while you're running NTPD. So at this point, I am clearly already scarred for life. I was before I started this process as well, but things have just got worse. Some options don't trigger any of my GDB breakpoints. So that's odd. They're still changing the hardware somehow. But they're not calling inB or outB from they're not calling these functions. So what are they doing? So I started stepping through instructions in GDB. I broke on the last. The vendor was nice enough to leave the debug symbols in the tool. Or at least the function names were still there. I didn't have full debuggability, but anyway, it was nice of them to do that. This would have been more miserable otherwise. So I was able to step through in GDB, and I was able to discover that when I stepped past a certain point, the next instruction was an address that was not part of my text region. It was not part of the application's executable code. But it was clearly code. If I disassembled it, I saw code. And this was when I realized why it was only available as a 32-bit binary. It was opening/dev/mem, which provides access to the system's physical memory. The kernel won't let you map most of that, but because obvious security disasters. But it does provide access to the firmware, and it provides access to certain PCI devices. So it was opening dev/mem, and then it was m-mapping a chunk of physical memory into its own address space. And when I looked at the address it was mapping, it was, in fact, part of the firmware. So this system was, in fact, mapping the BIOS into its own address space and then executing BIOS code. I really deserve a medal for this performance. So GDB wasn't going to help me here, because GDB can't set a breakpoint on an arbitrary instruction. Needs another approach. An LD preload is a wonderful thing. LD preload allows you to intercept certain calls that an application makes and execute your own code instead. So what you can do is provide an LD preload library that takes IOPL, and then when an application calls IOPL, you don't actually do anything. So the application believes that it now has the ability to read and write to system I/O ports, but it actually doesn't. When it attempts to, it will take a segmentation violation, which would, in normal circumstances, cause the application to crash. But because we are brilliant people who I'm not actually sure where I was going there. Because we're awesome, we don't allow that to happen. We insert a signal handler that catches the segmentation violation, and then when we get into that signal handler, we decode the instructions around the instruction pointer, because the kernel hands us a stack frame that tells us where the code we're executing was. So we can read that out of memory, look at those instructions, and then we take the x86 instruction documentation. We work out every sequence of bytes that can perform an in or out to system I/O, and then we decode them, set IOPL to 3, which means that we can then do the port I/O, perform the port I/O, set IOPL back to 0, so the next one will still trap, increment the instruction pointer, and then return. And then the application continues. It gets the values it's asked for, but we're also able to print what it did. Hooray! This was not my idea. In fact, I used some code written by someone else to do this. So I take no credit at all for this concept. It's a great way of doing things. It's the only way that you can do certain types of debugging in a reasonable way, which is a terrifying thing. So what was the tool actually doing? And that was still an open question. I could now see every single port I/O it did, not just the ones that it was doing through its own functions. And it was accessing some I/O ports that were directly on the IPMI controller. If you look in LSPCI, you can see that some PCI devices have I/O ports as well as memory regions. And that is typically so the firmware can do access to this configuration space early in the boot process. Now, the access patterns it was performing were quite familiar looking. And then again, this was really quite upsetting once more, because after doing all of this, after laboriously finding out how to get a full trace of what this tool did, I discovered that the mysterious work it was doing was actually identical to the PCI configuration space access. The PCI config registers that it was touching were mirrored in I/O port space. The only explanation I have for this is that some of the values are required by the firmware before it's actually done any PCI configuration, and so it does the port I/O access in order to get them instead. But anyway, that was a little bit upsetting. At this point, I actually had to borrow my neighbor's recycling bin. Anyway, now that I had all of that, I was able to write a utility that could set all the firmware values. I knew how to program every single type of them. I could reliably set values. If I rebooted the system, I saw that those values had, in fact, been changed. I could turn the TPM on. I could turn the TPM off. If I wanted to, I could now write a small hard-coded utility that I knew would work on this system. The question was, what if I wasn't running it on that system? What if I was running it on a different system from the same vendor that had the same programming model? Where was the XML file that it generated coming from? So I ran strings over the binary. Strings is a small tool from binutils. It basically prints out any sequence of printable ASCII characters that's longer than a configurable number. So it'll print any string and also a bunch of garbage, but any string will appear. And none of the XML data was in the strings output. So it wasn't creating the table itself. That information was coming from somewhere else. But there was one thing I saw. So this final line here, is anybody able to guess what that is? Right. It's a list of command line options. It's an argument to getopt. So I had run the tool with --help, and most of these options were documented options. But that one at the end, the capital D, lowercase d, that was not documented. Was, in fact, an undocumented debug flag. And in fact, when you set that, the program printed out every single thing it did. There now follows a short period of silence. So, and one of the nice things I saw there was it hunted for a specific DMI table. DMI is a specification that allows the firmware to provide typically static tables of data to the operating system. Some of these are standardized, some of them are vendor-specific. So for instance, there's a standard one that gives you the system vendor name, the device model, a list of pieces of hardware attached to the device. So that's nice and straightforward. And then vendor-specific tables are obviously vendor-specific. And obviously, the one it was looking for was vendor-specific, because what else would it be doing? This turned out to be fairly uninteresting. The DMI table was way too short to contain anything particularly interesting, but it did contain a value that was clearly a physical address. And then, OK, you map that address, and then you get another table. And this table contained the entire list of strings and values that had been used to create the XML table, the XML file. So success. I now knew how to find the set of options. I knew how to obtain the set of values that each option could be set to, and I knew how to access the address of each option, so I knew whether to go through PCI space, whether to go through IO port space, whether to go through CMOS, and which register to write there. That was mostly just tedious. It was a matter of staring at a dump of the table, writing some parsing tools to dump it out to make sure that I understood enough of the table. I didn't end up decoding all of it. There's a small number of bits that I didn't figure out, but they didn't seem to matter that much. I don't think I've killed any systems with this, so they can't have mattered that much. Anyway, so here is a summary of the behavior of this tool. It accessed PCI configuration space in a racy manner. Hooray! It accessed CMOS space in a racy manner. Hooray! And it executed BIOS code from user space. Hooray! Anyway, I took what I'd learned, and I re-implemented this 250 kilobyte user space binary, which was full of race conditions that could potentially destroy your hardware, and I re-implemented it as an approximately 1,000 line kernel driver. Hooray! And normally that would be the end of the story. I would have mailed this to LKML, and we would have merged it, and everybody would have been happy. That's not actually what happened. Things, well, as you can tell, because this driver hasn't actually been merged into the kernel, but you would think that this meant that something had gone horrifically wrong. In fact, things got quite a bit better. I got an email from someone at the vendor in question who was interested in ensuring that future generations of the hardware didn't behave the same way, and wanted to make sure that it would be implemented in a way that was compatible with Linux. So there's ongoing work to make sure that that happens. So that was actually wonderful, and that's a genuine hooray. At which point I felt that I deserved a drink. So I think at this point we've got about 10 minutes for questions. So please, if you have any questions, ideally questions that relate to this presentation, though I will potentially be able to answer other questions you have about life. Mark.
What were communication with the vendor where you were able to identify the developer of this program?
OK, the question was, in my communication with the vendor, was I able to identify the programmer who created this? I did not feel that actually tracking this person down would do anything to improve my life, because were I to somehow sink into some sort of haze of red mist, it's difficult to write a significant amount of free software from inside a jail cell where they don't allow you to see light, let alone a computer.
Just interested in how long the process was to...
How long did this take? So I ended up doing this in... Most of this work got done, it was either June or July last year, which in Boston is brutally hot and incredibly humid, and therefore I was completely incapable of sleeping. So most of it got done then, and it took about 3 or 4 days of pretty much full time. And when I say pretty much full time, looking at about 16 hours rather than 8. The rest of the time, as I said, I couldn't sleep, so was probably drinking. It was under a week for the most part, and then the most tedious part of actually writing the kernel driver was all the string parsing that I had to do, which, having reconsidered this and having actually communicated with the vendor, I'm now thinking that doing string parsing in the kernel is a bad idea for several reasons, and instead we'll probably just dump the data out and then parse that in user space, and we'll just have a driver that provides a mechanism for providing race-free access to the hardware rather than one that actually implements all of the code locally.
Can't you just do the config space through SysFS?
Man, can't you just do the config space through SysFS? Yes, but that's not sufficient. You need to also go through IO port. You need the IO port access to the PCI device things, and you also need the CMOS access, which you could in theory do through /dev/nvram. I suspect what actually happened was that this tool was a port of the Windows code that probably has a stub driver to grant the same sort of levels of access. Or alternatively, it was written before. No, we've always had PCI config space access, haven't we? Yeah. So I don't know why they didn't do it in a more reasonable way. You could do this entirely in user space in a safe way, potentially, but it would be really miserable.
For you, having to deploy a current driver makes it a little bit harder than just deploying through.
Yeah, and there's some downsides to doing it in kernel. You could potentially do some of this in user space, but there are some benefits in doing at least a hybrid implementation where the hardware access is in there. There's already a driver in the kernel for driving the different bits of functionality on this card. So as it's in there, seemed like a reasonable thing to do. Steve?
So you said that the DMI tables contain all values, and so the things you can set and what they can be set to. But you also said the XML strings weren't in the binary.
Right.
Where did the XML DOM come from?
OK, so where did the XML come from rather than the values? The XML, when I said the XML string, sorry, I meant the interesting strings that were contained within the XML. The binary did produce the XML, but it did so using these strings that it had read out of the table reference from the DMI table. Does that answer your question?
Yeah.
Something benefit. Why the hell, even with IO extend, are we allowing user space programs to write to PCI and CMOS?
Why are we letting user space write to PCI configuration registers and to IO ports and execute BIOS code, that kind of thing? The answer is mostly X. Pre-KMS, we did graphics drivers in user space because that sounds like a brilliant idea. Well, part of it was that Xorg was fairly kernel agnostic. So it needed to have methods for handling direct access to hardware when the hardware could be the same over different operating systems. So basically, yeah. Now that you've got KMS, this is actually functionality that you can completely disable and have a completely working Linux system. In Fedora, when we use UEFI Secure Boot, we in fact disable all of these accesses because they're horrifically insecure. So yeah, you don't need them anymore. They're there mostly as a result of historical accident.
Is anything you've learned in this process useful for other devices or other systems?
Is anything I learned here generally useful for other devices or other systems? Potentially. There are some. Most other vendors do provide a web mechanism for accessing these configuration things, which is actually closer to what we wanted from the systems. But some of these vendors, as well as providing the web access, also provide user space tools that can be used to configure from the host side. So they provide both mechanisms. And I would hope that none of them are quite this bad. But maybe they are. I haven't needed to look because it didn't directly impact what I was doing. But you would probably use the similar techniques in order to figure out what they were doing. Except ideally, you would find out where they have a secret debug flag that tells you everything they do first.
Did you try contacting the vendor? Have any luck at the start of the process?
Did I try contacting the vendor at the start of the process in order to ask for documentation then? I didn't, because my experience of doing that has generally not been great, and often it would probably have involved filling out a sufficient amount of paperwork that it was faster to reverse engineer it than it was to just actually fill in forms. Also, the problem is if you speak to the vendor first, then the vendor may say, don't reverse engineer this or we'll sue you. If they haven't said that to you, they might still sue you, but it's a little less straightforward for them to do so. I'm a big believer in this kind of instance of asking for forgiveness rather than permission. Anyone else?
Trying to be charitable, were there any reasons that would have led the developer to actually write it this way?
Are there any good reasons for the developers who have written it this way? I mean, parts of it, the executing code from the BIOS was presumably because that is the specified way of doing it from the vendor. Technically, my implementation is probably violating the spec by doing what the BIOS does rather than executing BIOS code. But actually executing BIOS code in the kernel would probably be frowned upon. So being charitable, that aspect of it is potentially legitimate in a sense. The rest of it,
It's probably a DOS tool, actually.
OK, Ben suggests that it may have been a DOS tool, and that's actually quite plausible. It may well have been originally written for DOS, and then this is a port of it. That would explain why it doesn't use any operating system functionality other than a very limited set. Obviously, in DOS, you can do this, and there aren't any races because DOS doesn't do anything.
There's one question for IoT.
Yeah.
Was this less or more fun than fruit flies?
Was this more or less fun than fruit flies? So context here, I used to be a fruit fly geneticist. Fruit flies are undocumented. There's a certain level of similarity between the two topics. However, fruit flies, the code that fruit flies execute is not written by anyone competent at all. And in fact, it clearly wasn't, in fact, written by anyone. It works as a result of multiple side effects. It basically exploits buffer overflows in all kinds of things. Sometimes you read straight off the end of some code into some other code, and miraculously it carries on working anyway. And we don't have the faintest idea what it's doing, really. We've managed to figure out that, well, this bit does that, and this bit does that, and somehow you then end up with a fly. But beyond that, it's... The other fundamental problem dealing with fruit flies, though, is that code stays still while you're trying to work on it, and fruit flies don't. In fact, fruit flies will do things like die. And then you need to wait for more of them to be born, and then you need to wait for them to grow up, and then you need to separate the male ones from the female ones, and then you need to make sure that they're carrying specific mutations. This is way better. Did I look for a debug flag in the fruit flies? No. If anyone does find an undocumented debug flag in fruit flies that, when set, causes fruit flies to tell you what they're doing, that would be excellent. So, we're out of time. As you said, thanks for coming. I'll be around for the rest of the week, and I'm giving a keynote tomorrow.
Can I get one more round of applause for Matthew Garrett and Matthew Garrett?
Thank you.